So this little talk is going to be on calculating light emission probability from complex geometry. So often when you're designing something like an OLED or a transistor that emits light, you want to know if a photon is generated in the centre of the device, what's the probability of it escaping the structure and doing something useful. And you can do this with ray tracing, and this is what we're going to be talking about in this little talk. The problems are often quite complex because not only do you have sort of multiple layer structures, the layer structures may not have a uniformly sort of flat surface. They may be bumpy, various types of roughness. You might have done some nanolithography. So the calculating the escape probability of light from these structures can be quite complex, and that's what we're going to tackle in this little talk here. We're going to do it in a practical way, so you can be able to repeat these steps and do it at home and change this structure for whatever structure you're doing and making in your lab. So you can download the software from this address here, and any questions or bug reports, please get in contact with me here. So making new simulation. So once you download the software and install it, click New Simulation, select Ray Tracing and Escape from Film. So this is the demo that we're going to be going through here. And it's all set up effectively to work, and you can sort of edit that to your heart's content. So once you've double clicked on that and saved it to your home directory, you'll get this window, and there's various components of this simple structure we're going to be simulating today. You can see, so what it is a ZNO layer, so zinc oxide layer, and it's composed of two parts. You've got sort of a very perfectly square box of ZNO at the bottom here, and you've got a rough surface that's an AFM image that I've processed to be 3D that's on top of it. So what this is simulating effectively is some top of sort of perfectly flat film with some roughness on top of it. And on top of this I've deposited a perfect layer of P3HT. So this is effectively smoothing off this rough surface. And what we're going to do is we're going to emit light at these green parts here. So these are arrows, which I'll show you in a minute in a bit more detail. And we're going to calculate the light emission. So these are slightly embedded in this film, but they're actually arrows if you look at them in the actual simulation. So this is an arrow, this is an arrow, this is an arrow, this is an arrow, and this is where our light's going to be emitted from. This is a detector, so this purple grid is a detector, so any photons that go through there will be counted and detected. And you can see it's a grid by 8 by 8, so you can think of it as like a CCD camera with sort of 8 by 8 pixels going to detect the light from our little arrows that's coming out of the device. So just in dimension of simulation, so let's go through this. I think I've covered this in other little chats, but let's repeat it here just for good measure. So you can change all the devices in this simulation are built up from layers. So because this software is usually used to simulate structure with multiple layers, everything's based on the device having layers. So you can set up the layer structure using the layer editor here, so you can select how thick your layer is in meters, and you can also select the material that your layer has in it. So in this case we've got this top layer is P3HT and this bottom layer is ZNO. So this layer here is actually this green box. So this semiconductor layer, this P3HT, is actually a green box here, and the oxide is the grey box here. If you want to change the X and Z dimensions of this substrate, you can do it using substrate XZ size, which you select here. So you can sort of change that. This is currently 2 microns and 2 microns respectively. And if you want to edit this this sort of rough surface, which is ZNO, what you do is you right click on the surface and you click edit, and this will bring up this object editor, and you can change the various properties of this layer using the object editor. So top of the object editor, so we're just looking at this window here that you brought up by clicking edit. Top of the object editor are the object properties. So you've got this offset, so this is sort of actual position, and this is relative to the layer. So this red thing actually sits inside this green box, so it's sort of a sub-object within the layer. So everything's relative to that green box. And I'll just go back to the main picture actually. So the idea is effectively your device is made up of layers, but you can insert into these layers other objects of any type. So you can see we've got an offset of basically 0, it's almost zero, on the X, Y and Z axis. That sets the object size, so it's about 2 microns by 2 microns 2 microns, and that's its height. And then these objects can be repeating, so if you want to, for example, do a lattice or something like that, or some type of nano indentation, you can actually repeat this object, and this number of objects is how many repeats in the Y and Z and X direction. Currently it's just repeating once, because we just have one copy of this object, and you can change the distance between these repeats using this dy dx. And then below here we've got things like the object colour, well, it's red, brilliant. And then we've got the object shape, which I'll talk about in a moment, and the optical material, which is zinc oxide. You edit these just by clicking here. So if you go to the shape database, so I'm not going to bring that up right now, but if you click shape type AFM image, you change this and you select photonic crystal, you'll be able to change how this sort of top layer looks like from this rough surface to this sort of photonic crystal thing. And the point is you can import any type of structure you want just by clicking AFM image, or just by clicking shape type and importing the structure that you want to import. And I'll probably talk about that more in another video on where I'll talk about the shape database. Optical sources. So these are the optical sources I mentioned before, these green arrows, 1, 2, 3, 4. If you right click on those, it can be a bit tricky sometimes to make sure your mouse is on them. If you right click and go edit, you'll be able to edit the optical sources. So it'll bring up this window here, which is the object editor again, but in it this time we've got things like, I'll move on to the next slide. So as before, we've got things like the X, Y, Z position and number of repeat objects. So you can see this time we've got four arrows, 4 light sources, 1, 2, 3, 4 light sources here, and we've actually gone, okay, repeat this object once in the X, once in the Y, and 4 times in the Z. And then moving down to the bottom, you've got this is specific for this light source. You've got theta and phi steps. So this is how much light is emitted in the various axes of light source. So you can scan through 360 degrees and then 180 degrees in the other direction. You'll emit in sort of 360 degrees round the round the light source. Final thing about this light source is you've got to have, for these ray tracing simulations, you've got to select illumination type X, Y, Z. That just means it's sort of a free light source that you can position anywhere. And also what's worth noting is, although you can access the light source by right clicking on these green arrows, you can also access it by clicking on the light source in the optical tab. Optical detectors. So this is the optical detector, this purple grid that I mentioned before, and you can think of it as sort of a CCD camera that's going to detect the light coming out of our film. You can edit this by clicking optical detectors here, or indeed right click on it and click edit. And you can change the number of sort of cells in that thing, the sort of pixels in that thing by clicking, by changing the X and Z values here. So examining the results. So once you run the simulation, so if you just click run simulation and double click on detector there, let me just close my email, and click on detector there, what you can do is you can examine in effectively 2D how the light has hit the detector. So this is showing effectively we've got some light hitting the detector in the centre of it. So if we go back to the sort of the vision of the simulation, maybe we can find a better picture. I think that's as good as we get actually. You can see the light effectively hitting this detector in the centre of it, and this is why we've got this sort of light detection in the centre of our sensor. There's another 3 files that are kicked out here. There's detector ABS and detector efficiency. Detector ABS is number of counts of detector detected. So if a photon's emitted from the centre of the device and 100% of that light makes its way out of the device, it'll detect a 1. If only 10% makes its way out, it'll detect 0.1. And we've also got the detector efficiency file, which is the light detected over the light emitted. So it's sort of an efficiency of the light's being coupled out to it. And it looks like this. So this is for this particular material. So we've got effectively some type of absorption dip where not much light is making out of the device, but about 500 nanometers. But either side of that, we seem to be getting quite a lot of light out of our structure. What's next? So the final thing, or one of the final things I want to look at, is this file called Ray ABS stats. So that's kicked out when you run a simulation. So if you double click on that, and then you'll get effectively plots of the fraction of light that's been absorbed in each layer. So for example, we can see in the semiconductor we've got about 80% of the light sort of absorbed, and then it drops down. And then for the other layers, so we've got the insert, which was the rough surface, and we've got the oxide sort of back part to the simulation. We're sort of getting less absorbed. So we look at sort of the absorption of the light in each layer. So setting up the wavelength range. So quite often, so you see, quite often you want to set up sort of what wavelengths you want to simulate over. So in this case, we're going between 300 nanometers and 900 nanometers, and we're using 20 steps. So you can see the points here. So it's sort of from 300 nanometers all the way to 900 nanometers. And these are wavelength points that we're going to be simulating. And you can access this through the optical mesh button in the optical simulation window. So finding the simulation world. So it's just worth mentioning briefly the simulation world. Around the simulation that we're doing, there's sort of this world box that effectively represents the maximum minimum bounds that light rays and things can be in. If you click right button, then view, then show world box, you'll get this box that shows you sort of where your device sits in the world. If you want to change it, you can do this by clicking all the size that you can on substrate X, Y size, and then if you click on world size, and then you can change effectively it's a multiplier you've got here to push to increase the size of the box. So in this example, if we go back, you can see the sort of this distance here is about 3 times from here, from this device to the top, is about 3 times the device height, and hence that's a 3 there. So you can play with these numbers, and if you click apply, it'll apply that to the box, to the simulation. So that's it really. It's just a brief run through effectively how to do optical simulations, how to figure out what's happened with the light that's being scattered out of the device, and how to sort of import various how to import various structures into the device and sort of play with the simulation. So I hope you find that useful. Drop me any comments below, or drop me an email, whichever you like, and I'll be happy to answer. Thank you very much.